YouTube viewers, it is Crystal here. I'm going to be presenting you the last video on time series analysis and forecasting in R, because we've covered quite a bit. We covered some techniques used in time series analysis and forecasting, such as smoothing techniques and a REMA model and Holt-Winters model. And now what we're going to do is we're going to talk about how the linear regression model can be used in forecasting. So basically what it is you don't really 100% need to use linear regression in forecasting in R, because you've got the ARIMA model and the Holt-Winters model built into R. But let's just say, hypothetically, you were using another language such as Python that doesn't have time series analysis and forecasting models built into the program, and you were using a library such as sklearn that doesn't have a time series analysis functions, you could always try out a linear regression model. But failing that, you could always use another library in Python, such as stats models or SciPy, because stats models is a statistical library designed for Python, but it had originally been part of SciPy. But they took it out of SciPy and made it a separate library. So if you're using R, you don't really need to use linear regression, but this is a good academic exercise that you can use just in case you're using another language, and that other language doesn't have the ARIMA model or the Holt-Winters model in it. So a linear regression model can be used to perform time series forecasting, because regression can extrapolate trends and seasonal patterns. Linear regression forecasting is good for clear trend and stable seasonality. Linear regression forecasting is not good for nonlinear patterns, changing seasonality, autocorrelation, heavy series, volatility clustering, and long-range forecasting. So as you can see, that linear regression is very limited in the time series forecasting that it can do, but it still can do time series forecasting if you're in a bind. So now I've got a program, and we're going to go over this code and the program just to show you how you can actually use linear regression for time series forecasting. So the first thing we're going to do is we're going to create our time series, and we're going to set the seed to do that. And the reason why you set the seed is so every time you run the program, the variables will be initialized to the same value. So you type set.seed brackets 1, 2, 3, and you can put any number you want within the brackets. Now we're going to define the time. It's going to be 1 to 60. So your time is going to be a vector with numbers 1 to 60 in it. And now we're going to define our trend. Our trend is 0.4 times time. So basically what's happening is your trend is moving upward. Now we're going to put a seasonal component in there. So 10 plus sine bracket 2 times pi times time divided by 12. Okay, so the sine is the sine function. It gives you a sine wave, and it's what gives you your seasonal component in this time series data. Now we're going to inject some noise into the data. So noise becomes R norm. That's a randomly sampled normal distribution of 60 samples with a standard deviation of 2. So now we're going to define our y variable, which is your dependent variable. And y variable becomes trend plus seasonal plus noise. And now we're going to create our time series data. So TS data becomes TS, which stands for time series, brackets y, comma, frequency equals 12, comma, start equals a vector from January 2021. So that means you've got 60 elements in the time, and so the frequency is 12. So every 12 elements, you're going to start a new season. So 60 divided by 12 is 5. So that means we're making data over a 5-year period. Now we're going to build a regression data set. So DF, that's data frame, becomes a data.frame brackets y equals s.numeric TS data, comma, t equals 1 to length of TS data. And so you know that the length of TS data is 60. Sine 12 equals sine brackets 2 times pi times brackets 1 to length of TS data divided by 12. And cosine 12 equals COS, that's for cosine, brackets 2 times pi, brackets 1 to length of TS data divided by 12. So sine and cosine are a little bit different in their appearance. They're still cosines, but they have different frequencies in their appearance. And it's been a really long time since I studied sine and cosine, like maybe more than 45 years. So we're going to fit our linear regression module. Fit becomes LM, that means linear model, brackets y tilde t plus sine 12 plus cosine 12, and data equals df. So just wondering, where is the t? Yeah, t. The t is in this data frame. And then we're going to summary fit. So we're going to make a summary of this linear regression model. So this is a summary of the linear regression model. So you've got your call is your formula is LM brackets formula equals y tilde t plus sine 12 plus cosine 12 and data equals df. You've got your residuals of min, first quarter, median, third quarter, max. You've got your coefficients for your intercept. The t, cosine, and cosine are different columns in the data frame that you've created. You've got your residual standard error being 1.862 on 56 degrees of freedom. So you calculate your degrees of freedom as being 60, which was the original number, minus 4, because you've got t, sine 12, cosine 12, and you've also got y. So 60 minus 4 is 56 degrees of freedom. You've got your multiple r squared is 0.9631. Your adjusted r squared is 0.9611. Your F statistic is 486.9 on 3 and 56 df, that's degrees of freedom. Your p-value is a very low value, being 2.2 e to the negative 16. And we've also calculated our root mean squared in another part of the program. And that root mean squared is going to be 1.799086. So that's something to keep in mind. Your root mean squared. So now we're going to forecast the future trends. So H becomes 12. So future T becomes length of TS data plus 1 to length of TS data plus H. So that's going to be 61 to 72, I think. And then future DF becomes data frame brackets T equals future T, and sine 12 equals sine brackets 2 times pi times future T divided by 12, and cosine 12 equals COS, that's for cosine, brackets 2 times pi times future T divided by 12. And then we calculate our future values. Becomes predict, so we're going to predict on that, brackets fit, and new data equals future DF. And we're going to plot actual and forecasted data onto a chart. So plot brackets TS data, comma X lim, that's the limit on your x-axis, is a vector with C 2021 to 2026. Y lim, that's your limit on your y-axis, is range of brackets C, brackets TS data, comma forecast values. Your main is your title of the chart, being linear regression time series forecast with a line length of 2. Your forecast TS becomes TS, that's time series, brackets forecast values, comma start equals C, that's vector, 2026, comma 1, so that's January of 2026, and frequency equals 12. Lines, you're going to put a line in the chart, brackets forecast TS, comma color equals blue, line width equals 2. You're going to put a legend in the chart, is brackets top left, comma legend equals a vector you've created, says actual and forecast, and color is another vector, which is actual is black and forecast is blue, and line width is 2. And then we're going to calculate the RMSC, because whenever you're working with a regression model, the goodness of fit test is generally RMSE, which is root mean squared error. And so what you want to have is you want to have the lowest error that you can get. And that's how they calculate how well that model is. So you've got fitted values becomes fitted brackets fit, and RMSE becomes square root of bracket mean brackets DF $y minus fitted values squared. And then we're going to print the RMSE using tat. Tat is a print function, brackets RMSC, comma RMSE, comma N, which stands for next line. And then we're going to run the program. And this is what we've got. We've got linear regression time series forecast. So you've got your actual values that we started with, which are from the years 2021 to the end of 2025. And then you've got your forecast from the January 2026 to December 2026. So you see that we've got our actual values and our forecasted values. You see that you've got a trend which is moving up, which is positive, and you've got your seasonality So so basically what this time series data looks like, it looks like a very crude sine wave. So you've got your seasonality as well. So that's it. That concludes this video on how you can use linear regression for time series forecasting. And we've done it in R, but you can always try it in another programming language if you like, such as Python. I mean, the two major languages that I program in are Python and R, because those are the programs that you're going to need to be proficient with if you're going to be a data scientist. But some people program in other languages, such as C. And a long time ago, maybe 35 years ago plus, I studied C and Pascal and BASIC and those types of languages. But if there's any new languages coming up, which I'm sure that there will be new languages coming up, you can always give this a try and see how well it works. So this is the final video on time series analysis and time series forecasting in R. The next video that I make is going to be on non-parametric models. But that's not going to be for a little while because I have to enter my Kaggle competition, which I do that every month. So thank you so much for watching my video, and I hope you got something out of it, and I hope you get something out of my future videos as well.